Good morning, good afternoon and good evening. Thanks for joining my talk. I am Burkhard Ringlein from IBM Research Europe in Zurich and the Friedrich Alexander University in Erlangen-Nuremberg. And I'm happy to present you the results of our research about using disaggregated FPGAs for function as a service. From our perspective, we could observe two megatrends in computing research throughout the last years. First, cloud computing has evolved from simple online storage and web services into the new way of providing any kind of IT service. Compute resources are increasingly consumed via public and private clouds, and traditional applications are modernized using scalable microservices and function as a service or FaaS offerings. Those offerings have helped many companies to greatly simplify the development and operation of their cloud-based application and services. And this trend is also reflected in the number of scientific publications in the last years. But well, we are here at the cloud conference, so we all know that. So let's focus on the second trend I would like to highlight. The emergence of domain-specific hardware and specialized accelerators due to the end of Dennard scaling and the slowdown of Moore's law. This trend got emphasized by the rise of artificial intelligence, or AI, and the performance-demanding requirements of AI-based applications. Hence, GPUs, Field Programmable Gate Arrays, or FPGAs, and application-specific integrated circuits, in short ASICs, are offered by today's major cloud providers as well. Therefore, we are in the age of configuration. Okay, one closer look. What does this age of configuration mean? As you had heard for sure before, some convenient laws have come to an end. The scaling of the power density did stop, the scaling of the transistor density is slowing down, and unfortunately, not all parts of an application can be executed in parallel. Therefore, the use of many cores has only a limited impact in performance increase. This relates to the somehow pressing question if this is the end of the line, the end of the possibilities. Luckily, the answer is no, because we can still leverage performance based on specialization, which is the trend mentioned before, and that's why we are in the age of configuration after the ages of clock speed and parallelism. Consequently, FPGAs are used more and more due to the good deal they offer in terms of flexibility, performance and efficiency. So, one could assume that the two megatrends, serverless computing and heterogeneous accelerated infrastructure, would seamlessly lead to new offerings for accelerated serverless computing, but this has not yet happened. That's why my colleagues and I explored in our research this topic, and I will present in this presentation the results of our research about the missing components of FPGA-based FaaS. Okay, good. Then let's close this gap and let's use FPGAs in the cloud. Well, sadly, despite the good deal FPGA offer, there are still some challenges if it comes to the cloud deployment. But first, an overview of existing cloud infrastructure for FPGAs. There are two groups. Most FPGAs are offered in a closely coupled way, so via PCI Express attachment in most cases. This forces a lot of vendor and device dependencies onto applications, as depicted with the green highlighting on the left-hand side. On the contrary, recent research did free the FPGA by breaking the close coupling and created disaggregated FPGAs, as shown on the right-hand side of the figure. Those disaggregated FPGAs did show to have significant advantages in terms of flexibility and energy efficiency, and they could be provisioned faster. Consequently, disaggregated FPGAs appear to be a good match for function as a service, since disaggregated FPGAs are not connected to a network interface card or NIC, they have to have an integrated NIC. And this integrated NIC shortens the network latency and consequently the event processing time. For example, related research showed a UDP validation and routing time below 0.1 microseconds for disaggregated FPGAs. Similarly, a TCP connection can be processed in less than 0.6 microseconds. Additionally, since there is no CPU or other hardware that must be booted before the FPGA, disaggregated FPGAs have a very short cold boot time, which leads to better serving of application requirements. In our work, we were able to show a cold boot time below 7 seconds. But we will discuss the results later in more details, of course. Okay, great. Then let's use disaggregated FPGAs in the cloud. That's better, but there are still some vendor and device dependencies, as shown by the grey box in the middle of the right-hand side of the figure. Those dependencies still limit the possible flexibility and efficiency of FPGAs in the cloud. In addition, recent research also did point out that the disaggregation of FPGAs comes with additional constraints, especially if it comes to data center integrity and security. Probably the best environment for FPGAs would it be if FPGA applications could be developed vendor independent like software applications, as sketched in pink and blue in the middle of the figure. Considering this background, our contribution in this research is the enablement of true FPGA-based functions as a service, where the FPGA instances can be managed independently of CPUs and can be switched on and off as frequently as the application demands it. We simplified the development and deployment of cloud FPGA applications by enabling forward and backward compatibility within the FPGA on binary level. This includes the decoupling of security critical parts of the design. As mentioned before, our contributions lead to the provisioning time of new cold-booted FPGA instances to below 7 seconds. Last but not least, we integrated our solution in an existing OpenStack installation. Before we move into the details, I would like to show a brief illustrative example of the type of functions and setup we had in mind for our research. For example, we offer some image denoising as a service. Therefore, the user posts a request containing the image and the respective service URL pointing to our FaaS framework frontend. The framework validates the request and realizes that the corresponding service had scaled to 0 before, and therefore the framework invokes a new instance. In our experiments, we use 3 different types of hardware to process this request and compare the performance and resource parameter. For this type of workload, we would expect a speed up between 5 and 20 and energy savings of up to 80% due to the use of disaggregated FPGAs. So quite a valuable offering. Okay, for such an application, how does the FPGA design look like? Usually, the FPGA design gets split into 2 parts, a platform-specific part, which is usually referred to as shell, and an application-specific part, which is usually referred to as role. The shell contains all security critical functionalities as well as the control paths or runtime control cores. The advantage of this design pattern, called shell role architecture or SRA, are that low-level details of I/O are abstracted and all the different privilege levels could be enforced. Because if the shell is some kind of wrapper to the role, it controls all physical inputs and outputs of the role and there is no way around it. This is especially true if parts of the FPGA are configured after each other, called partial configuration. But the discussion of those features would go beyond the scope of this presentation, unfortunately. As a summary, due to its advantages and solid engineering, SRA design patterns are used frequently by all major FPGA platform providers and cloud vendors. However, the SRA pattern also comes with some disadvantages. Both parts depend on the same interface. Really like some Lego bricks that must fit together. Hence, once such an interface is released, it is some kind of frozen, because changes to it would require changes of all already developed applications. Since we are talking about hardware, this means the interface is frozen on all levels down to the physical connections within the FPGA. On the other hand, all the FPGA applications are no longer developed in a monolithic way and depend increasingly on third-party intellectual property cores and runtime environment. As a consequence, a large number of different shells need to be available. Okay, why is this a problem? If more than one shell exists, it means that after booting the FPGA and prior to the deployment of the application, the right shell must be selected and configured. The term configured means in this context to write the binary FPGA description into the FPGA hardware and therefore to tell the FPGA what to do. Selection and configuration of the shell takes time, which slows down the provisioning and, in case of disaggregated FPGAs, limits the flexibility and efficiency since a disaggregated FPGA boots with the last used shell. And if this shell is not the right one, it must be changed and the FPGA rebooted. This increases the provisioning time further and demands more boot memory and control logic for the disaggregated FPGA. Hence, if used for large deployments, SRAs undermine their intention and lead to a greater complexity and incompatibilities. Our goal is to bring the flexibility found in container and package-based classical CPU platforms to FPGAs in the cloud, while at the same time simplifying the deployment process for cloud vendors. Therefore, we introduce the Mantle design architecture as depicted on the right-hand figure. This design pattern adds a third layer between shell and roll and therefore repeats the original engineering motion behind the SRA. This third layer is called dynamic platform logic. But adding one layer is not enough, since there would still be dependencies in the control path depicted as green lines in the figure. So, if you take a closer look at the interface between the static and dynamic platform logic, it could be observed that we use a standardized bus for the control path. Yes, two management cores that share the responsibilities of managing the control path within the FPGA. So the design-specific control path is offloaded to the management companion core, or MCC. The MCC is then controlled by the FMC via the mentioned standardized bus, or Axi4-like bus. Consequently, the static platform logic is not impacted by the new dynamic platform logic and can stay the same. And since we talk about hardware, this is true for all the layers down to the physical pins within the FPGA again. If thinking about it, it becomes clear that this share of responsibilities between FMC and MCC requires forward compatibility of the FPGA management core, so that the static platform logic can control all future dynamic platform logics or mantles. Okay, this is done using a new instruction set architecture within the FMC. The motivation to develop a new instruction set architecture is threefold. First, reuse logic for different API commands, and second, the ability to load new code from the MCC when a mantle is deployed. In addition, this allows to offload mantle-specific instructions to the MCC if the API command demands so. The MCC introduces itself with a standardized header table similar to the Linux ELF format. The table consists of pointers to the dynamic code library and the new API commands that are part of the MCC, as well as other pointers and metadata and the type of comments that could be offloaded. Okay, that were a lot of low-level details of the FPGA designs, but what are the global implications of the Mantle architecture? So let's come to the data center architecture. Building on our previous research, the data center architecture consists of three levels of management. First, controlling what's happening inside the FPGA. This is done by the just presented FMC and MCC. But the FPGA can't control everything, even not the disaggregated FPGA. For example, it cannot boot itself. Hence, there is a second level that controls the power state and network addresses of a group of FPGA, also called FPGA sled. Third, all chassis or sleds in a data center are controlled by a single FPGA resource manager. This management level controls mainly the ownership and the physical health of all FPGAs in a data center. Our architecture is built on RESTful APIs and interfaces with an OpenStack deployment as presented in detail in our previous research. Now, how does this help the user? The Mantle architecture design pattern enables a user-focused deployment. The user just needs to specify the requirements of his FPGA app using JSON. One example of such a JSON is given here on the right-hand lower side. Then the FPGA resource manager checks the available resources and deploys the necessary mantle if necessary, based on the specification of the JSON. Consequently, the user can use third-party IP cores for FPGAs like Python or JavaScript packages and can focus on his or her application. After discussing the high and low-level details of the composable Mantle architecture, I will present now the results of our in-depth evaluation. To evaluate our proposed system architecture and design flow, we compared two FPGA-based systems and one CPU-based system, similar to the setup of the shown illustrative example. First, we evaluated the Mantle architecture on the IBM Cloud FPGA or VF platform. This disaggregated FPGA platform features mid-size network-attached standalone FPGAs that can be managed using RESTful HTTP APIs. The system architecture was shown on the previous slide, and here you see a chassis with 64 FPGAs and 2 leaf switches, guaranteeing a 10 gigabit Ethernet connection to all FPGAs. The FPGA board contains, besides the FPGA, 16 GB of DRAM and a small flash chip here on the right upper side from which the FPGA boots. This flash chip can contain only one shell or static platform logic. Second, to compare our research platform with commercial available technologies, we also tested the possibilities using one AWS Elastic Compute Cloud F1 instance. An F1 instance is a CPU FPGA heterogeneous platform where the FPGAs are tightly coupled with a CPU via PCI Express. Last, to compare with CPUs, we used one bare metal server containing 2 Intel Xeon processors running Ubuntu. Using these platforms, we will evaluate the main goals of the proposed mental architecture, that are, first, the improvement of the configuration, provisioning and boot times, continued by the improvement of building times. Finally, we will evaluate the potential resources, overhead or performance penalties. Okay, let's start with the configuration times. As explained earlier, a configuration is the process of telling the FPGA what to do by writing a binary file containing the synthesized functionality to the SRAM cells of the FPGA. FPGAs can also be configured partially, so that, for example, only the right upper corner of a chip is configured, or only the red zone here, while the remaining hardware, so for example the lower part here, continues to run uninterrupted. Usually, configuration is done using the industry standard debugging bus JTAG. As can be seen in the table, using the FPGA control path to do a partial configuration always outperforms the JTAG process. Furthermore, splitting the design so that the static platform logic is configured during booting and then the dynamic platform logic, so the orange box here, and the app logic, the red box, is then configured partially afterwards, cuts the provisioning time or switching costs even further. In this example, using the mantle architecture, the configuration of all functionalities would take roughly 1.2 seconds, while using the classical JTAG approach would take nearly a minute. This leads to our next experiment to evaluate the true end-to-end provisioning time. Hence, we measure the time of a cold boot until the application execution is starting on FPGAs or CPUs, as it would be if the functional service framework requires new instances. As can be seen in the table, the cloud FPGA platform outperforms the bare metal server by a factor of 40 and the AWS F1 instance by more than 10 times. For AWS, we could not request FPGAs attached to bare metal servers. Consequently, the measured results in the table are not completely fair, to our disadvantage, since we compare a bare metal CPU with a virtual machine and a bare metal FPGA. However, we think the comparison is fair enough to exhibit the impact of the proposed architecture in combination with disaggregation on the provisioning time of FPGA instances. Based on these results, we model the behavior of large functional service of rings that has a dynamic request load. The results can be seen in the figure on the right hand side. The result exhibits the advantage of the faster response time of our composable and disaggregated mantle architecture. By contrast, the classical FPGA, so the AWS F1 instance with a closely coupled CPU or VM for the platform management, instead of the proposed static platform logic within the FPGA, cannot scale as fast or meet the requirements as represented by the AWS F1 experiment. Next, we evaluated cold boot and switching costs. The efficiency of a functional service offer depends also on boot time and switching times. Hence, one of the main goals of our research was to increase the execution efficiency of an FPGA-based function as a service. Therefore, we measured the total time to execute 3 different functions on one device from boot to power off. To avoid confusing application-agnostic boot and switching times with application-specific acceleration, we replaced the real execution times for all platforms with the same placeholders, namely 10, 25 and 45 seconds. The results show that our mental architecture finishes executing all functions when the AWS F1 FPGA starts the first step while the CPU is still booting. In addition, the time actually spent on execution is close to 90% for our architecture. This result underlines the general advantage of standalone FPGAs and composable FPGA designs. Fourth, we verified our expectations that building the app logic alone decreases FPGA synthesis place and route time by 80% as shown in the table. In addition, we wanted to evaluate the overhead of the composable mental architecture concept in terms of FPGA resources. The result for FMC and MCC within an example design is similar to our illustrative example. The resource usage of an FMC and MCC are below 5% of the available resources. This very limited overhead supports the idea of offering user-friendly dynamic mental extensions. Finally, we calculated the potential performance penalty for cloud FPGA using the mental architecture. We wanted to ensure that we do not achieve significant efficiency gains for execution and deployment at the cost of decreased performance, because this could render the acceleration useless. To avoid the bias of a few selected applications, we decided to calculate the Ringlein model of the cloud FPGA platform instead. In this figure, the attainable performance of one cloud FPGA before and after the introduction of the mental architecture is shown. For example, the image denoising of our illustrative example would have an operational intensity around 1. The Ringlein indicates that the potential peak performance of one FPGA application is only reduced minimally by around 1%. With these motivating results, I would like to summarize. We can observe the general trend of FPGAs stepping into clouds due to their energy efficiency and flexibility. Deploying them as standalone, disaggregated and compute nodes enables a seamless integration with scalable cloud services. But despite the trend to serverless computing for classical CPUs, FPGAs lack the integration into function as a service frameworks. With our research, we aim to close this gap by proposing the mental architecture pattern. With its dynamic 3-layer architecture, the mental architecture offers a forward and backward compatibility while simplifying the design and deployment environment for FPGA-based function as a service offerings. Our evaluation shows an increase of the execution efficiency by factors of 2 to 4 to approximately 90%, even if the FPGA is used for just 80 seconds. Additionally, using partial configuration and the self-management capability of the proposed FPGA management cores, the cold boot and provisioning time of new FPGA instances is reduced by factors of 13 to 43 to below 7 seconds. We hope that our research highlights the promise of disaggregated FPGAs for cloud offerings and helps FPGA-based function as a service becoming a reality. With that, thank you, and I'm looking forward to the discussion.